So this my research was recently published in an international journal. So the journal name is AMIS Mathematics. So today I just want to discuss about my research, my intention on the research paper, and future studies, so on. So my name is Sadia, and these are my other authors on this research, and I'm the adjunct lecturer of Brac University. And firstly, abstract. I want to discuss about the work on my paper. We all know that trees are very important for our ecosystem, like producing oxygens and supporting our ecosystems, and our ecologically also tree very important. But there are many different kind of threats for our the growth of our trees, but beetle attacks is one of them. So in our study, our main goal to describe the beetle attacks on our forest, and we also discussed about two other descriptions, which is our harvesting and wildfire. So in our model, in our study, we just solved this model. We found the equilibrium points, and then we also discussed the stability of the equilibrium points, and we also discussed the reproduction number of our model, then which reproduction number and their properties to describe the beetle population of our in the forest system. And additionally, we have to control the beetle attack in our forest. So that's why we do many optimal strategies to control our beetle attacks. So in this system, we also do the pesticide to edit the variable in our model to do the uh, uh, forest ecosystem management, and we also do the sensitivity analysis to describe the influencement for the variable on our ecosystem. A particular variable can how can the influence our beetle attack in our forest. So that's why we do also the stability analysis. And uh, overall we focus on the tree plantations systems and how can we do better work for to establish our forest ecosystem management. So these are some keywords for our research, and these some visual representations of our keywords. This is the beetle. In our study, there are different kind of beetles in our world, but in our study we focused on mountain pine beetles. This is mountain pine beetles. Mainly we studies on Canadian forest system. So in Canadian forest system, how can a mountain beetle can the attack the forest, how the population dynamics works, and this is the wildfire system, and this is the harvesting, and this is the mainly the pesticide. Introduction. Beetle eater can hurt our ecosystems, our forest, our also forest means it doesn't mean any tree. It can also hurt our animals in the forest. Then what is harvesting? Harvesting means removing a certain number of population at a given time. So we also know, we have to know the removing of the trees at a from the forest at a given time, the effects of removing trees in the forest, and sometimes wildfire. Wildfire, there are many causes of wildfire. It can be natural, it can be man-made, but extreme heat can cause wildfire. So the effects of the wildfire on our forest also described in our model. So mainly the objective of our discussion is the negative effects of the beetle attack in our forest with two disruption, which is harvesting and wildfire. And we also focused on the pesticide use to control the beetle attack so that we can save our forest system. So case study in Bangladesh, we just briefly do some case study in Bangladesh. In our Bangladesh, it is 8th most densely populated country in the world. So there are many forests and there are many forest sectors to control our forest ecosystems. So as beetle attack is a great threat to our forest growth, so different kind of forest ecosystem took different kind of plants and different kind of time periods to control the beetle attacks, so they can manage our forest ecosystem. And these are some examples of the plans or strategy which was taken by the forest sectors in our country. And finally, we want to describe our main model, which is beetle tree interaction model. So it is a system of ordinary differential equations which is impressed by the predictive tree model with nonlinear incidence, and this is called a beetle tree interaction model. And we again we can say there are two descriptions, which is harvesting and the fire. In our model here, M is described the density of our tree, and N is N describe the density of beetle part with part tree, and R is the growth rate of tree, and Rn is the reproduction rate of our beetles. So here Gk, which is the fraction of trees which is killed by the beetles, and R is the defensive rate of the trees by the beetle. So here L, E is the proportionate loss of the trees by the harvesting, and L is the response of trees to the harvest, and P is the response of the trees to the fire. Here QM, this is the proportionate loss of trees for our fire. Here Km, which is the carrying capacity of our trees, which is carrying capacity. Carrying capacity means any maximum number of trees which can sustain in a region at a given time. And this is the carrying capacity of our beetles in that region. And B and C, which is the effects of harvesting, and C is the effects of fire on our trees to defend the beetles. And this is the reciprocal of the density of trees at which trees defensive rate goes to the peak point. So, and Qn is the loss of beetles for the fire, because fire does only damage our trees, also damage our beetles in our forest. And this is some description which is I told in the previous section. So in our model there are too many variables and parameters, so we want to do some dimensional analysis. Dimensional analysis means we have to recycle the variables and parameters by a system to estimate the physical units. So that why we do dimensional analysis? We do dimensional analysis to reduce our parameters and variable numbers, so that we can calculate easily and do the numerical estimation so properly. That's why we do the dimensional analysis. There are many mathematical expression for our dimensional analysis. If anyone need some more description how we can do this, anyone can contact with me. Our here N is the ratio of M by Km. So as the unit of N is tree and also K is tree, so tree by tree is unitless. That's why in this process we do the dimensional analysis for the other variables or parameters. So this is our final model for our study, and this is the initial value condition for our model where t or time is 0. Then equilibrium point, we know that for the equilibrium points we have to do the derivative equal to 0. So if we do this, we find two equations. If we do this mathematics, we find two equations, this and this. So if we put the value in this equation, we find the value of M. It is called a boundary value equilibrium point. As or we can also say this beetle free equilibrium points, because there is no beetles in the forest. So this is our boundary equilibrium points. But if there is beetle in our forest, then it is called it the coexistent equilibrium point or endemic equilibrium point, because there is beetles in our forest. Then from this equation, we can also find the value of m where n is not 0. And also n is greater than 0, because we know that the density of any population cannot be negative. Again, if we putting the value of in this equation, then we can find after some calculation, we can find this kind of expressions or equations. We can rewrite the expression in simple way. If we consider this as f1, consider this f2, consider this as f3, and consider this as f4, then we can write this equation in this way. As here all the variables are positive and there is a negative sign, so we can say this the whole expression f1 is less than 0. So if we put f of n equal to tends to 0, we can say this the whole expression as this is n to the power 3, so that this term is more stronger. So we can say f of n is minus negative. If we put n equal to 0, the all the term this term is 0, so there is only one term which is f1. So if we consider this is f1, this is f1, so we consider if this is our f1, we've considered if this term is greater than this term, then if we input the value of n equal to 0 for this term, if this term is greater than this term, so only f1 we can say that f of 0 greater than 0. So we can say if the real continuum theorem or intermediate value theorem, we can say if 1 is less than 0 and 1 is greater than 0 for two kind of condition, we can say at least there is n for which this is 0. We consider this n as n star, which is our endemic equilibrium point and n star. If we for n star, we can also find m star, and m star must be greater than 0, because again the density of any population cannot be negative. So we can say if there is beetle, so also we can find any tree in the forest system. So we can say if this condition applied, so there exists an endemic equilibrium point which is m star n star, and again m star greater than 0, n star is greater than 0. So we can consider our reproduction number is this basic reproduction number in this way. Our basic reproduction number for stability analysis, we firstly do the Jacobian matrix. How can you do the Jacobian matrix? Yeah. This is our main model. If we do consider this as G1 and consider this as G2, so our Jacobian matrix is do partial derivative, we can do the Jacobian matrix. So firstly derivative this with respect to m and n, then derivative this partial derivative with respect to m and n. So we can find the Jacobian matrix in this way. So for this model, this is our final Jacobian matrices. So as we find two equilibrium point which is at beetle free equilibrium point or boundary equilibrium point, so we put the value of this equilibrium point in our Jacobian matrix, and we find for this equilibrium point the J0 Jacobian matrix. Then if we consider this term as u1, this term as u2, this term as v1, which is 0, and this term is v2. So we rewrite the denote in this way, and we can do the characteristic equation for this Jacobian matrix, which is this is our characteristic equation. This is the trace of the Jacobian matrix. This is the determinant of our Jacobian matrix. For trace, this is the summation, and for determinant, as here v1 is 0, so u1 v2. This is our determinant for the Jacobian matrix. So we here rewrite any theorem for our model to find the stability analysis. As every variable is greater than 0, we can write if this equal to greater than 0 and this term is less than 0, then the boundary equilibrium point in E naught is stable, and otherwise it is unstable. So as this is our quadratic equation, we can find the root of this equation by doing this kind of formula. So here this is our root of this equation, which is our eigenvalue. So if the eigenvalues are negative, or if it is complex number and the real term is negative, then the eigenvalue is stable. So if it is stable, we can apply two conditions. Trace must be less than 0 or determinant must be greater than 0. So for this equilibrium point, it is our Jacobian matrix. So determinant, we find the determinant is this. So u1 v1 greater than 0 for the stability, and this for the trace u1 v2 less than 0. So we proved our condition. So we proved our condition, two condition for the established of E naught. Otherwise, this is the condition for the stability. So if any of the condition is not satisfied, so we can say it is unstable. So if any condition is not satisfied, as trace is greater than 0 or determinant is less than 0, so we can say it is unstable. Then if it is unstable, if E naught is unstable, so there exist endemic equilibrium points, which is M star and N star. So this is our another theorem, when the ato is for this condition, this is stable, and for this condition this is unstable. How? Previously we write for this condition, if this condition is applied, we know our basic reproduction number is this is our basic reproduction number. So we know for the stability of the Beetle free equilibrium point or the disease free equilibrium point, R naught must be less than 1. Less than 1. So for the stability of the Beetle free equilibrium point, the reproduction number must be less than 1. So if it is less than 1, so we can write so we can say if this condition satisfied, this is stable. And similarly, it is unstable when R naught greater than 1. So that's why we can say when this condition is satisfied, E naught is unstable. If it is unstable, there is endemic equilibrium point. So for the endemic equilibrium point, this is our Jacobian matrix, and again we can write this as W1, this as W2, this as Z1, and this as Z2. Similarly, for the condition of the stability is crest must be less than 0 and determinative must be greater than 0. So let any region, we consider any region which is this, and in this region there is endemic equilibrium point which is E naught. So, and we consider E naught is stable obviously when R naught greater than 1. So, if we apply this condition, so we can say that E naught is globally asymptotically stable. So, we consider region as in this way where m is greater than 0, n is greater than 0. We consider any scalar function, this is our scalar function, and multiply the scalar function with our main model. So, with this is our main model. These are two ordinary equations in our model, multiply with this scalar function and defined as dy and dz. Then we partial derivative of the dy with respect to m and partial derivative dz with respect to n. As q also greater than 0 and also n greater than 0. So, we can say this whole term is negative. So, we can say this is negative. Again, if we do negative terms, we have to do this term also negative. So, how can you do the negative term if alpha n gamma 1 plus whole term is less than of this? Then we can say this term is also negative. So, this is our another model where there is beetle attack in our forest, but there is no harvesting condition. So, there is only the fire condition in our model. This is the initial equilibrium points. For this model, similarly by previous calculation, this is our boundary equilibrium point and the coexisting equilibrium point is same. By almost similar calculation, we for this model we find the endemic equilibrium point m star, and this is our endemic equilibrium point while m star represent the tree and n star represent the beetle. So again for our this model, this is our Jacobian matrices, and this is Jacobian matrix for our E naught, and this our Jacobian matrix for our E star. Same, the presence of harvesting disruptions where there is beetle attack in our forest but there is no fire in our condition. There is only harvesting disruption in our model. So similarly for this model, this is our boundary or beetle free equilibrium point, and for the endemic equilibrium point, this is our endemic equilibrium point, and the endemic equilibrium point is stable when this condition is applied. Similarly, this is our Jacobian matrix, and this is our Jacobian matrix for E naught, and this is our Jacobian matrix for E star. Mathematical examples. So mainly we study for two kind of equilibrium points, which is boundary equilibrium point or beetle free equilibrium point, or coexistent equilibrium point, which is endemic equilibrium point. We collected the data from different kind of papers which is published. So, and mainly the data is for Canadian data. Some of the data is assumed for our calculation and some of the data is estimated for different kind of calculations. So So presence of both disruptions when harvesting and wildfire also present in our condition, and also beetle attack is uh, stable in our model. So beetle free equilibrium point, this is our equilibrium point where m naught is 0. So there is no beetle in our model. So there is only 2 disruptions. So and it's then not my that kind of questioning that updating over Iragune that should obviously as an introduction because the much supply reduction it's instigate data some change in utility with that more globally in terms of yes, my model can work for globally. Just maybe the parameters of the variable will not change, just the data will change for the particular results. If we can say do Bangladeshi data, Indian data, the parameters remain same, but the data will be changed for that result. So in these conditions, there is no beetle in our model. So for this equilibrium point, if we increasing the value of QM, we represent the death rate of the trees, and if we increasing the value of KS, which represent the death rate of the trees for the harvesting, and this death rate of trees for the fire. If we increase the value represent gradually, we can say the value of M decreases slowly, and again we can, if we increase the value of QS, which represent the death rate of the trees, the value of M decreases as M is so we can say as M decreases, the capital letter M also decreases, which is called the density of trees. So that we can say that the density of trees is decreases for the condition of harvesting and wildfire. For the endemic equilibrium point, in this condition, there is also beetle attack in our forest. For the endemic equilibrium point, there exists beetle in our forest. So, for the existence of the beetle, the number of beetle is increasing. The effects of beetles and harvesting and wildfire, the number of trees is decreases, and it decreases more compared to our previous model, as there is beetle attack in our forest, but in this condition there is no beetle attack. So the beetle attack for our trees decreases more rapidly. So if we increase the value of K, which represent the amount of trees which is killed by the beetles, so if we increase the value of K, we can say the value of M decreases more rapidly. So as similarly as M is Km, so the density of trees also decreases for the increasing value of K. This is gamma 1. If we increase the value of for gamma, if gamma 1 is 15, firstly we say that it decreases. If we for the time being over the time increases, then the value of N is increases, and similarly for if we increase the value of gamma 1, it increases more fastly. So gamma 1 represent the amount of beetles at which the beetle tree density goes to its peak point. If we increase the value of the gamma 1, the trees cannot defend the beetles in our forest. So for after increasing the value of gamma 1, as they cannot defend the beetles is increasing day by day. For the effects of beetle attack, the trees density is decreases in our forest. Presence of fire disruptions where there is no harvesting effect in our model. So as QM is the death rate of represent the death rate of the trees for the effects of fires. So similarly, as we increases the value of QM, the value of m is decreases. So the capital letter M is also decreases. So the density of trees is decreases. This is a visual representation of the wildfire. So in this condition, the endemic equilibrium point is works. So as beetle is increases, the effects of beetles and fire, the density of M, which represent the density of trees, decreases. Similarly, for the value of K increases, the amount of trees which is killed by the beetle increases. That's why M is decreases. So the capital letter M is also decreases. This is the harvesting disruptions. In this model, there is beetle attack and the harvesting disruption works, but the fire is not working in our model as QS is increasing day by day. So the death rate of trees for the harvesting is increases. So that's why the amount of M is decreases over the time period. For the endemic equilibrium point, M increases. That's why N increases. That's why M is decreases. And in this factor, we can say some oscillation or some dynamics in our beetle populations. How can we say that as we cut the trees in our forest, so it can reduce the amount of beetles, but there can produce different kind of trees in that result after the harvesting. So which if tree produce rapidly, so it can produce the amount of beetles. That's why there can some oscillation in the dynamics of our beetle population. Then the optimal control strategy. Our objective is to manage the beetle attack in our forest so that we can manage our forest ecosystem. So in our model, we add new variables in our model here, which is U. U is the growth rate of the tree when we reduce the beetles in our forest by using the pesticide in our model. And W is the amount of pesticide which is applied in our system, and G is the death rate of the beetles by using the pesticide, and QM, which is maximum amount of pesticide which can be used in our model. Similarly, by doing the dimensional analysis, this is our final model. So objective is to increase the amount of pesticide to manage the beetle attack in our forest and to increase the tree amount. So this is the boundary, this is the upper bound for the W, and the for time, this is the highest number of time. So this is some condition for our W, which is the amount of our pesticide in our model. So this is our objective function. We have to maximize our objective function, and this is our integrand of the objective function, and this is the Hamiltonian function. How can you find this? As it is G1, consider this G2. If the condition satisfied, we can say this is a maximization problem and we have to do the maximization problem. So, if partial derivative with respect to W and equal to 0, we can find the amount of W, which is the maximum amount of W which can be applied to maximize the pesticide to decrease the beetle attack in our forest. And if we do the second partial derivatives, this is minus, this is negative term. As this is negative term, we can say this is maximization problem. If it is positive, then it is will be minimization problem. As our target is maximization problem, so we can say our considerable optimal function is good for our model. So this condition is applied for the maximization problem. So for the we can find this by partial derivative of h with respect to m and n, then multiply by -1. Then this is some data which also collected from different kind of papers, and some is assumed and some is estimated by different kind of calculations. And in this graph we see that if we increasing the amount of W, which represent the amount of pesticide in our model, we can say the using of pesticide, the density of the beetles is decreases, and the amount of trees is increases day by day. Sensitivity analysis. This is our sensitivity analysis. In our sensitivity analysis, we describe how the any parameter can affect our model. The parameter we consider our parameter for the sensitivity analysis is the pesticide parameter, which is W. So here we consider UI for this expression, where X or I is the state variable. The state variable are M and I. Our P is the parameter. In this sensitivity analysis, we consider the parameter as W, which is the represent the amount of the pesticide. So here, if we do this, which is the Jacobian matrix of our main model. So after some calculation, if we do the solve the model, we find 2 points for the value of M and N. So we can say that if we time increases, the amount of W N increases more rapidly compared to U M. So we can say it as this represent tree and this represent beetle. So by using the pesticide, the tree decreases more slowly than the beetles. So summary. So trees are very important in our forest ecosystems, as beetle is a threat to our forest. So we in our study we try to describe the beetle attack in our forest with two disruption, which is harvesting and fire. So we also try to describe the attack, and we also try to minimize the our attack by using the pesticide condition in our model. Uh, so these are the summaries of my study, and thank you for listening.